It's really great to see a bunch of my old friends here from graduate school and coworkers, because part of this Center for Emergent Superconductivity is in collaboration with the Argonne Group and Brookhaven National Laboratory. So what I'll be talking about is, okay, so I'll just give you an overview. The talk will be really fun and easy for the first 20 minutes, and then a little more serious, and then I'm going to blow you away, because I have to, just a little bit, because I have so many experts here. But if I'm looking around and seeing you're not getting it, I won't get to the blowing away part. I'll save that for private discussions. Anyhow, what we do in the Center for Emergent Superconductivity is study high-temperature superconductors. How can we make superconductors better? And so I will mention at the very end of my talk our Materials Genome Initiative on how we're planning to design new ways to create and predictive design of superconductors. And anyone who knows anything about the field goes, ha, 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 that's impossible. And part of my talk will be showing how it is impossible. We also are trying to understand the mechanisms, and also very important is some of the applications. So I'll be talking about some of the applications in power transmission, power generation, and power storage. And this power storage here is, we call SMES, superconducting magnetic energy storage. And I'll mention all of these at least quickly in here, so we see how important some of these aspects can be to secure our future energy. Now here's the outline. I'll give you a quick review of what superconductivity is, because I'm going to assume, since it's the colloquium, not everyone remembers that. And the need for a better superconductor. Better does not just mean high TC, high superconducting transition temperature. You also need to carry a lot of current, and I will stress that point. I'll talk about the history of the discovery of superconductivity, which is a heck of a lot of fun. And then I have my own little soapboxes, which I like to stand on. And I'm going to stress this, and this is both for the non-expert and the expert. I am changing the definition of conventional versus unconventional superconductivity. And I think I can explain to you all why I'm changing that. When I have time, if I have time, I'll talk about my own measurement, which is a renewal of point contact spectroscopy, which will help us differentiate between the conventional and the unconventional superconductors. And then, can we actually tame that serendipity and towards a materials design? So, two properties of a superconductor. The first one is, there's both a type 1 and a type 2, that as you lower the temperature, or lower the field in this case, you get below a certain temperature where the material conducts electricity without any power loss at all. You can do that, okay? And you also have something that shows that the material is not just a perfect conductor, it's a superconductor. A perfect conductor and a superconductor are distinct. When Meissner and Ochefeld, and we call it the Meissner effect because Ochefeld was a graduate student, so if there's any graduate students in here, graduate. This perfect diamagnetism, and I'll give you an example here that really shows that it's different. And in fact, this is long-range quantum mechanical behavior. And here's something taken out of an old book, Rosinas and Roderick, which I love to teach out of. And what we have is showing how a superconductor is fundamentally different than a perfect conductor. This is the superconductor in different stages, and this is the perfect conductor in different stages. Let's start with the perfect conductor, because that follows Maxwell's equations in the way we understand them. If we take a perfect conductor at a higher temperature, so it's still got a finite resistivity, and we put a magnetic field on it, the magnetic field lines will penetrate. If you lower the temperature to where it becomes perfectly conducting, what happens? Well, Mr. Maxwell dictates that those magnetic field lines get frozen in place. So then if you remove the external magnetic field, you're left with a little magnet. A superconductor, it behaves differently. We put on the magnetic field above the critical temperature Tc, and then lower the temperature, and this Meissner effect occurs, which literally forces the magnetic field lines out. Now when you remove the field, you're left with something that is not magnetic anymore. So we see that going through the same phases, the final states are different. This is how I like it, because it's a very experimental way we explain this is different. And this was what we show, it was proven early on that there's something funny going on here that must be quantum mechanical. Now, I want to stress something in type 2 superconductors, because we wouldn't have MRIs and we wouldn't have any kind of applications that most of us know about without type 2 superconductors. And that is that a type 2 superconductor does allow some penetration of the magnetic field into the material. And we could think of that as these little lines of magnetic field in the material. And then what happens, you get a supercurrent vortex around that magnetic field line that shields the rest of the superconductor. So a type 2 superconductor is still superconducting with little magnetic field lines going through it. Now, the center of those vortices where the magnetic field lines are going through it are not superconducting. Those are in the normal state. So if those vortices are allowed to move, they will be moving that normal material and dissipate energy. So a good superconductor is one in which the vortices are pinned. And we spend a lot of time worrying about that in our research in the Center for Advanced CES, the Center for Emergent Superconductivity. So here are some applications. Here's an application of diamagnetism. I still haven't learned how to do this with this thing yet. So what we have here is a superconductor, of a high-temperature superconductor. And this is just the erbium, one of those high-field magnets. And we can see how well pinned it is there. It really holds up there. If you try to float two permanent magnets, it's not a stable configuration. You have something called Harshaw's theorem, which says two permanent magnets cannot form a stable configuration, and you need something else if you want to make something levitate and be stable. And in fact, the Japanese have made a prototype maglev train with a high-temperature superconductor. So there's some real advantages to that. And I also want to say that in the 60s, when I talk about many of the applications that we have, in the 60s, the Japanese also had a levitated train made out of conventional superconductors. And they always were proud of saying it only goes a kilometer, but it goes far enough to take our funding agents for a ride. Now this is the fun part. Now, since you've had this great lecture, the sound isn't working. It happened again. Should we plug it and unplug it?
Doctor, thank you so much for joining me. Now this is, ladies and gentlemen, are you ready? Then please welcome from the physics department at Ithaca College, Dr. Matthew C. Sullivan and the quantum levitator. Doctor, thank you so much for joining me. Now this is a quantum levitation track, correct?
It is indeed.
All right. Well, thank you so much for coming on to help me crush Jimmy with quantum levitation. Nation, as I'm sure you know, quantum levitation refers to the phenomenon whereby the magnetic flux lines flowing through a type 2 superconductor are pinned in place despite the electromagnetic forces acting upon them. I learned that from the inside of a Snapple cap. Now, Dr. Sullivan, can you confirm that if my ice cream quantum levitates, it is undeniably the ice cream of the future?
Absolutely. That's just science.
Okay, excellent. All right, here we have some of my Americone Dream. It's available in mini cups, which Jimmy's is not, okay? And I will confirm, that it is delicious. And now, are you ready to send my ice cream into the future?
Certainly.
All right. Okay.
There was a switch.
Ice cream of the future, engage. It's levitating! It's levitating! Here, put it down for a second. There you go. Oh, Jimmy, look. Look, Jimmy. It's levitating. Eat it, Fallon. Eat the future. We'll be right back. Hit it.
I actually showed this at Rick Greene's Festschrift, and Matthew was in the audience, so he got a kick out of it, so I got my picture taken with him. It's very clever. Anyhow, moving right along, now you know everything about superconductivity. Why do we need new ones and better ones? Well, there's a few reasons. One is this, the fundamental research. I never, ever, ever thought I'd be in a field this long. It is, as I say at the end, seductive and consuming. And I'm going to say again later on that I really believe that the correlated electron problem and the way to design high-temperature superconductors is the biggest question of physics today. And it's really fascinating, lots of broken symmetries. It's complex, it's interesting. It's been around since about 1952, okay, and it's unsolved. Many applications exist. MRI, has anybody ever taken MRI? I think all of us have by now. You get to go inside of a superconducting magnet. Now, how cool is that? And accelerators, I just got another email from someone to collaborate on that. Anything high frequency, because superconductors are natural frequency voltage mixers. Fusion research, here's a niobium-3 tin wire that's used in the ITER project in France. Better would be transformative for renewable energy. Grid, turbine, SMEs. And if you want to make a large magnet, and the Mag Lab is in the process of designing and hopefully building a 65 Tesla magnet, you have to have high temperature cuprates to do that. There's no other superconductor that can take those kinds of high fields. And when I forgot to mention this here, this is what my postdoc advisor, who was John Rowell, measured. And this was planar tunneling into lead. And this is what we call the Eliashberg function. And this proved the electron-phonon coupling BCS theory of superconductivity. That's it. That's the order parameter. End of statement. We don't have that for high TC. But I'll tell you what we do have, and we do know a lot. And this is, if George is in the audience, I stole this from him a long time ago. Okay. This is not really the grid. This is the old Eisenhower highway system, but it tells you about where the population centers are and where the grid pretty much is. And the grid has been called one of the great triumphs of 20th century engineering. Forget the fact it uses 19th century engineering, but it's been pretty useful. And now if we want to use more renewables, we see we can mine the sun here. We could mine wind here, but we can see these bright areas, and that's where the population centers are. And we have to get those renewable energy to the population centers. And the grid is a clean and sustainable energy carrier. We don't want to be putting things in trucks and driving them. Now, the 21st century new challenges are the bottlenecks. You're trying to get all these energy into the small population areas, and I'll say how there's an advantage with existing high-temperature superconducting tapes. Reliability and quality, I love this number here. Resistive losses in the grid, and this is a little unfair because it even counts the transducing part, are $79 billion a year in the US. So if you can affect a few key areas, and I'll show you a good one coming up here, you could have a substantial impact on our energy use in the United States. And also, we plan to, at least the president plans to significantly increase the number of renewables we want to use in the United States. And so it's been pretty amazing the amount of engineering that has gone into making these wires. It started out, and most of the in-ground testing is done with what we call the Generation 1 wires. And what you have is a silver sheath, and you fill it up with the BASCol, bismuth, strontium, calcium, copper oxide material, and then you extrude it, and you get this multi-filament thing. And it's not very flexible. You can probably go like this with it. Very hard to make, very expensive. But they've been proven pretty reliable in ground, and it was a way to start. The pinning wasn't great, and they started making these things very soon after the discovery of high-temperature superconductivity, which was 1986. The second generation, they call it, are the tapes, and there's several companies that make them. There were these processes that were developed that were kind of like a plasma deposition, and you basically, over long length, have almost like a single crystal of the material, and they carry very high current under high fields. They've become very reliable. And the architecture, it's still a little bit, it's better pinning. It's still a complicated multi-layer architecture, so they're still expensive to make, but there have been a lot of improvements, and they're made much faster than they used to be. I also want to show you that about 2% of the cross-section is superconducting. And even though only 2% of this flat tape is superconducting, it still carries 5 times the power of copper does at the same temperature. So it can really help in the bottleneck problem. Another area that's become just new, and I'm just getting interested in myself because I didn't know much about it, are the new high-density APSCol wires. So this is the same material as was used here, but they're learning how to make these into very high density, and they're round. Now, an advantage of round wires over flat wires are important. It's because the way the magnetic field goes can affect the superconducting properties. And these wires, since they're flat, there's a lot of engineering that has to go into them so you can make sure that the magnetic field only goes through it in a certain direction. So when we build the high field magnet, we still haven't decided. We're doing tests on both the APSCol and the second generation YBCO tapes. So, but the materials are all pretty good, and I think these are mostly engineering questions right now. And this is pretty much what I said before, but what we're dealing with as far as large scale is cost, the anisotropy, which is making it difficult for the pinning, which I won't go into too much going on here. We need more research on the YBCO tapes, which we're doing in the center, and newer high-density APSCol wires. And we're going to be doing more of that, too, because it's all very promising. Here's the one thing that just reared its head again, its lovely head. And this is something that has been around since, 2009, and it was called the Tres Amigas power station or superstation. And it turns out in the United States, we have 3 separate asynchronous grids, okay? Mr. Tesla lost, Mr. Edison won, and everything is AC. And we have the Western Interconnect, the Eastern Interconnect, and the Texas Interconnect. And they're not connected. And it was brought up a year ago by the National Academy of Sciences that this becomes a national security issue, that we can't seamlessly send power across the United States. The plan was to build a superstation here where we would convert the AC down to DC and underground carry the power through superconducting wires and then invert it back up to the AC again, and thereby connect the grid seamlessly. And this would have been a great project because it was localized, you had a little bit cooled, and would have a high impact. The DOE stopped funding it around 2012, but I think it may be looked at again, and I'm very excited about this project because I think it would be important for the United States and our energy future. Now, I mentioned superconductivity as an energy carrier. And this is just to show, I was just in Paris, and in solidarity, I had to have a picture of the Eiffel Tower. It turns out that for power generation, it's really an advantage. The transformer inside of a turbine, when made out of superconducting wire, can actually be built at 1/5 the weight. And when you're talking about turbines that are the size of 737s, or the Eiffel Tower, it becomes important. So this becomes a real practical application. It's compact, it's small, not much to cool. And this is a little bit of the SMES. They're doing mostly this at Brookhaven, and this is not the power that we're going to need for the grid, but there's a few in-ground being tested. So this is an old technology that's just a bunch of toruses that collect the collect power and run it inside of a torus. And the advantage is that it actually is fairly fast in response. And so not only if you're going to be collecting power with your photovoltaics, you're going to have the day and night output from the photovoltaics, but they also tend to be a little bit noisy. And that noisiness, from what I am told by the people working on this, is actually slower than what the SMES can respond. So the SMES can pick up this energy that has a day and night change and a spikiness and accept this all and bleed it out at a reasonable time to the grid to make it useful. So those are some of the applications that we're looking at. And the other one, of course, are the high magnetic field ones. So now I want to go into the history. Any questions? You are welcome to interrupt me anytime. Okay, so yes? There are some prototypes being built. So I guess they're not, people don't like cryogens, but there are some being built. I can't tell you exactly where, but there are some. So, okay. History was the discovery. Superconductivity was discovered 104 years ago. Kamerlingh Onnes was not looking for a superconductor. It didn't exist. It was this, if you know the history, it was the race for the cold. How can we make really cold things? And he basically took the kind of refrigerator you have in your kitchen, but used high-pressure helium. And they were able to liquefy helium. And so after they did that, and that was 1909, he and Giles Holst, his technician, decided to see what would happen if we cooled down a metal. And they chose mercury. They chose mercury because mercury is a liquid at room temperature, and they know they could make it really clean. So they thought, maybe clean is good. And these were the three predictions. Lord Kelvin thought it would stop conducting. Matheson said this. Dewar said it would go to 0. Nobody expected that. So if you've ever been to a talk in by a low-temperature physicist, you've seen these ad nauseum, because we have to show that plot, But this is what he found was, at a certain temperature, the resistivity abruptly dropped. It took many years to show it was 0 resistance. It's easy to show small. It's hard to show 0. That took many years to show. And then Kamerlingh Onnes, after that discovery, went to try to see how much current could go through it, and he discovered critical current. And then he had Giles Holst start winding magnets with this, thinking we could make a really high magnetic field. And he used to get really mad at Giles Holst and say, "You're breaking the wire. What's the problem here?" Well, it turns out that the self-field from the magnet that he had wound was actually destroying the TC, destroying the superconductivity. So very quickly, Kamerlingh Onnes discovered critical temperature, critical field, and critical current. But he still hoped that it would have an impact on society. And there's a press release in 1913 in the Chicago Tribune where he announces you can hold a great amount of energy in these superconductors in this magnet, which is basically the SMES I was just showing you, to impact our world energy crisis. So here's a man that was slightly ahead of his time. Now, the history then moved slowly, and the Bell Labs people would probably recognize this guy here. This is Bert Matthias, and he just decided, I'm going to measure everything and mix everything together. And he discovered in 1952 the first new class of superconductors. He just mixed together cobalt and silicon, a magnetic and a semiconducting element, and it superconducted. So that was a surprise, but very interesting. And then over the years, he just invented more and more superconductors and classifying them. And when he classified them, he came up with rules, which I'll show you once again at the end. And the first two are correct. Transition metals are better than simple metals, and having a lot of electrons at the level where things carry current is a good idea. Those things still hold. But he didn't understand that there could be other classes of superconductors. So now, we know that high symmetry is not good. In fact, we like two-dimension is much better for the high-temperature superconductors. And stay away from oxygen, magnetism, insulating phases, and theorists. When in fact, part of our MGI is, well, first of all the high-temperature cuprates have oxygen. They're all at the border of magnetism. I'll show you the first example coming up shortly. The highest temperature ones have insulating phases, and we're working very closely with people like Mike and other people for our Materials Genome Initiative. Now, if anybody is interested in this history, there's a couple of papers here, and you can get these off the web. One is Jabal and Hume, Bert Matthias, a memoir, which talks about this very interesting man. And Pickett wrote an article which is very funny. It's called The Other High-Temperature Superconductor. And it was, what if Kamerlingh Onnes didn't cool down mercury the first time? What if he cooled down a high-temperature superconducting cuprate? So it's kind of cute if you want to do your homework on it. Anyhow, now, all of a sudden, something changed. And that is John Hume and George Hardy, who was his graduate student, discovered the first class of superconductors called A15s. And all they are an A3B structure, where A is a transition metal, okay? And these were the first superconductors to show a high critical current in a strong magnetic field. So you can put in several Tesla, and it would still superconduct. And you have to have that for applications. And over the next few years, Bert Matthias then discovered over 30 of these A15 materials, with the highest temperature one being niobium-3 germanium at about a 23 Kelvin TC. And my boss at Bell Laboratories, who was Jack Wernick, actually discovered a few of these things himself. I'll mention him again later on. I want to stress two things in this. This made it a better superconductor because it was higher TC and higher JC, but it was also hard to work with. And that's because it's a compound, and that crystal structure became imperative to it. So if you actually messed up the crystal structure, ground this thing up, hit it with ions down the road here, in the same building here, you would actually destroy the superconductivity or lower it. The crystal structure being sound was very, very important. So that went on to another important superconductor, and that is John Hume discovered that the Appleton labs in Rutherford Appleton labs in England had discovered a superconductor that was a random alloy, niobium titanium. And this thing you can squish around, you can hammer it, you could make wires of it. It's malleable because it's a random alloy. And this is the workhorse of the field. It has a lower TC and a lower JC in field than the niobium-3 germanium did or the niobium-3 tin, but it's easier to work with, and this is what people use. And that's what's in your MRI and many things. And when Jack Wernick, my boss, retired, John Rao said, high TC gets Nobel Prizes, high JC saves lives, which I really don't like that, but anyhow. Now, history. This, to me, is the beginning of unconventional superconductivity. By the way, for those of you that are experts in superconductivity, I'm being very provocative, but I stand by what I'm saying. So Franz Stieglitz discovered something called a heavy fermion and then a heavy fermion superconductor. And Gil Longeris and his group then did work on this particular one, cerium palladium 2 silicon 2. Now, why are they called heavy fermion superconductors? Because the fermions, the quasi-electrons that are carrying the current, are very heavy when they're measured thermodynamically, like using specific heat measurements. They're typically 50 to 1,000 times the electronic mass. For those of you that know a little bit of condensed matter physics, you can look at the crystal structure and get how the bands are, right? You do your electronic structure calculations, and you pretty much, using standard calculations, get the band mass of the electron. This doesn't work here. There's something else causing these electrons to get very, very heavy, and it is an electron correlation. So this, to me, was the beginning of real experimental measurements of highly correlated electron systems. This was also, what we discovered was that so this is the phase diagram. I'm going to show you a lot of these. That this is the y-axis, which is temperature. In this case, this is the x-axis, which is pressure. And Longeris was able to find the first domed phase diagram. So as you apply pressure, or in many cases, as you dope across this axis, you get a dome under which the material is superconducting. This is ubiquitous. Also, we see the superconductivity is next to a magnetic phase, probably quantum critical point down here, and the heaviness comes up here. So these electron correlations are way up here, way above superconductivity, and it's a correlated electron problem we haven't solved. Okay, so it's not going to be BCS electron phonon, something else. So I have to go on, and there's two reasons for using this slide. One is because we got to talk about cuprates, and we got to give a few examples where there have been amazing discoveries of superconductors. And for the experts out there, I am not talking about hydrogen disulfide today. This is a colloquium. Okay, we can talk about it after. So in 1964, in Marvin Cohn's PhD thesis, he actually did an electronic structure calculation where he thought strontium titanate should superconduct. And it does. It's a hard insulator. If you pull oxygen out, you can diffuse certain metals, transition metals in it. It superconducts. And I've studied that myself. This one I really liked a lot. In 1983, Len Mathis and Don Hammond predicted, based on a similar material, that this barium potassium bismuth oxide should superconduct. And then they went in Mike George's lab down the hallway and made it, and it superconducted. And then Bob Cava refined it to become a 40-degree superconductor. This, I believe, definitely falls into the unconventional superconductor regime. And then what people think was the start of the revolution, this beautiful work that Bednorz and Mueller. They wanted to see how Jahn-Teller effects would affect superconductivity. They came up with lanthanum, barium, copper oxide. Okay? And these guys, Paul Chu and M.K. Wu, came up with the YBCO, which broke the nitrogen barrier. I'll talk about Hasano in a second, but there are real, I don't know what you call it, but these guys are brilliant. These were amazing discoveries. They went out for them and they discovered them. But I also want to stand back and say, we have not proven the predictive design of superconductors. I know these guys. They're so smart, they scare me, okay? They are really scary smart, and they work like dogs. I mean, Paul Chu, I don't think sleeps at all. And they're always on the hunt for new superconductors. And every single one of these guys basically has a hit of one class of superconductors. If they had a second, I would believe in predictive design. Now, I'm not telling them not to do this. These are our successes. These are the only successes, and there's a few I've left out, okay? These are our only successes are the ones found by people like this. So don't stop funding this. But let's also try to find a way to make superconductors where someone like me can discover one that doesn't have this insight. Many of you are aware that in 2008, there was another discovery. Hasano was looking at transparent conductors, and he stumbled upon the new iron-based superconductors. People like to say, we went from the copper age to the iron age of superconductors. The cuprates had been around 23 years, and this was the first new class of high-temperature superconductors that broke the tyranny of the cuprates. In any case, it was really cool. And then Zhao pushed this thing up to 58 degrees. One of the reasons it was a big shot in the arm for the community, because for the first time, there was a second class of high-temperature superconductors. Does that mean there could be a third? So that's what we're all working on. And that's when I wrote this article, and I've been kind of getting together with people. Rick Greene and I have been doing, not related, going to meetings and sharing our ideas about how to design new high-temperature superconductors. At this point, it's still impossible. We don't know exactly how we're doing it. But we really are freely sharing our ideas because we think it's so hard to do and so important. That's the only way we'll get anywhere. It's much easier for me to go and measure a pseudogap and get a paper out than for me to design a superconductor. So that's sort of where we are with that. Now, what I want to do now is tell you some of my ideas that go into what I think defines a high temperature and unconventional superconductor. And I'm going to start with this DOE report, which some of the people in this room were on. I was on it too. And this is one of the famous DOE BRNs. And this one came out in 2006. It was the one on superconductivity. And there's this famous TC versus time plot. And here's what I think started the whole thing with the cerium copper 2 silicon 2. And I put everything on this line here to be, let me just step back and say, there's a little slip up here. This BKBO should be purple. But all of the red dots on this line here are a solved problem. Solved. Above TC, they're what we call Landau-Fermi liquids. We know how to calculate their properties: thermodynamic, transport, optical properties. Below TC, they are superconductors, and they all are electron-phonon-coupled BCS superconductors. And we have these great equations called the Bogoliubov-de Gennes equations that give us a mean field way to calculate all those things. Now, what this plot is missing, and I keep meaning to replot it, are many, many, many more families of superconductors that are not on this line here. Here's just a bunch of, here's the high TC cuprates. I have the iron-based ones on the next one. None of those are electron-phonon-coupled superconductors. And they all show pretty much the same kind of phase diagram, which I've mentioned before. This is the one taken out of that report. And what we have in this phase diagram here is this is temperature versus pressure or doping. Here's the superconducting dome under which is superconducting. I don't care if it's D-wave, if it's not electron-phonon coupled, there's some spin thing going on there, or excitonic, whatever it is. What we have found out is that those Bogoliubov-de Gennes equations work just fine there. You can put in a D-wave kernel. If you have multiband, you have to futz around a little bit with it. But pretty much, we understand what's going on down here. We might not understand what's causing the electrons to form Cooper pairs, but they do form Cooper pairs. So we do have an understanding of that state. Now, over here on the right side, the overdope side, the high pressure side, you return back to a Landau-Fermi liquid. Again, standard electronic structure calculations give you those properties. But when you go up here, there's all these little things, we call them strange metals, pseudo-gap, all kinds of weird charge density waves that have weird temperature dependences. I'm going to talk about electronic pneumaticity. At these high temperatures, as I mentioned before, the electronic structure is determined by the crystal structure in simple metals. In these things, you got a certain electronic structure at high temperature, you come down in temperature, and all of a sudden the electrons form stripes, or globs of sausages, or they get really heavy, or they form other kinds of interesting things. But there's some kind of correlation that goes on, which in some cases we know is a definite symmetry breaking. So here's my definition, conventional and unconventional, okay? So all conventional superconductors are the red ones on here, and all the unconventional are off of this, and they all have this kind of phase diagram, and they all have this electron matter up here. Okay? This is different than the definition a few years ago. So if you've read the definition a few years ago, was that the superconducting order parameter, which is the wave function that you square to get the gap. Okay? So you got some wave function, and you can write down that equation. If that symmetry of the superconducting order parameter is lower than that of the underlying lattice, D wave where you have plus and minus as opposed to S wave, that's a lower symmetry than a tetragonal lattice. So that was considered unconventional. But the iron-based superconductors are probably not D wave. They're probably something we call S plus minus, which is basically S wave, which is basically the same symmetry of the underlying lattice. But I believe they're still unconventional. They still have the same phase diagram. And what we find, and I'll spend a little bit of time talking about it, is that the electron fluid above TC breaks the symmetry of the underlying lattice. So, okay, I'm going to show you that. I'm not kidding you. Okay, conventional I'm just reiterating because I like my definition up on my soapbox. Okay. Conventional superconductors, TC is typically below about 40K, except for this new one I don't want to talk about because I don't understand it, but it's incredibly cool. Anyhow, below TC, Cooper pairs, as described by electron-phonon-mediated BCS, and Bogoliubov-de Gennes equations work just fine. Above TC, we can describe everything using as a Fermi liquid. Solved. Unconventional superconductors. TCs are typically under 165 degrees, and they have this ubiquitous domed phase diagram. Below TC, Bogoliubov and de Gennes still help us out. Above TC, on the right side, it's Landau-Fermi liquids. Above TC on the left side, it's a non-Fermi liquid, not even a near Fermi liquid. And that is what is unsolved in physics. Here's just a few. I could show you hundreds of these, but here's the cuprates, here's the dome, here's pseudogap, here's some iron-based, I'll show you some data we have from up here that shows the pneumaticity. These transition metal dichalcogenides they're just cool. They have these charge density waves that have this changing charge density wave as a function of temperature. There's organics. Here's another, anyhow, we can go on with that, but let me just go on. What is electron matter? I'm going to start by telling you what it is not. It is not a Fermi liquid. It is not, Peter's not in the audience, something that he did a lot of work on, a near Fermi liquid. It's something we call a non-Fermi liquid, something described for you theorists out there as having a real self-energy. General definition for me as an experimentalist is that the electron fluid has a lower symmetry than the underlying lattice. And an example, the easiest one, and the one I've worked on the most, is electronic pneumaticity. Oh, before I define pneumaticity, I want to say one more provocative statement, and that is about the high-temperature superconducting dome. Okay? I mentioned this is a Fermi liquid out here. It's weakly coupled. TC goes down. I mentioned we have strong correlations out here. TC goes down. So there's a lot of measurements that show that electron matter is actually detrimental. It robs spectral weight from the Cooper channel. But you don't get high TC without it. Okay? You want it, but not too much. So I believe there's going to be some delicate balance, and understanding that electron matter, in my mind, because you got to choose something, will help us understand high TC and how to design them. Okay, what is electronic nematicity? Well, this is a nematic single crystal. Things are, you have flowing in some directions, but you have a definite direction. It's what we call C2 symmetry. The same thing happens in an iron-based superconductor. But above a certain temperature, it's actually fluctuating nematic. So what we have here is these lines here are supposed to show the tetragonal lattice. You look down at the lattice, and it's square. And at a very high temperature in comparison to high TC, and a very high temperature, even in comparison to when it goes orthorhombic, the electrons they form these little sausages. Okay? And there's a lot of evidence that this shows. So that's the electrons become C2 symmetric. They have a fluctuating orthorhombicity. So if you don't know this, you're not going to learn it now. But there's a lot of data out there that shows these nematic phases exist. And what happened in our lab, this is when it first started with Ian Fisher, but I won't go into it here because if you don't know it, I don't have the time to go over it, but I'll show you what our measurement did. Okay, now I've got to go into point contact spectroscopy, just stepping back. How much time do I have? 8 minutes? 10 minutes? 10 minutes? Oh, I could go on forever. Okay. So I'm going to go on and define point contact spectroscopy. And I think I'll do this one first, then I'll go back. So Janssen, in 1974, wanted to do some tunneling into lead. So he decided to copy what McMillan and Rowell had done. And he made a tunnel junction, and he was measuring all the superconducting properties. And then he put a magnetic field on it to drive the lead normal. And he still saw the Eliashberg function. There's a theorem called Harrison's theorem that says you're not supposed to see that stuff if the material isn't superconducting. What was wrong with this picture? What was wrong with this picture was his junction. He didn't have a good junction. He had what we call pinholes in the junction. So instead of the electron tunneling into the normal lead, it was being injected into the lead without a barrier. So you're just injecting electrons in there. And what that allowed him to do was measure the phonon properties. I'm going to go forward again. I'm just changing the order here. Okay, so going back to what he was actually doing there, if you have an aperture that's very small, and you inject electrons into there, and you have phonons in there that are just like ball and springs, if you hit the right energy, you will cause some of those electrons to backflow at that energy. And what they did is that they just mapped out phonon, magnon, and other bosonic spectra in a whole bunch of metals. And so that was pretty much solved. I want to stress that this is up here to show you, this is one of Janssen's old papers, when in fact, this is a really small effect. Not only does this aperture have to be small in the mean free path, okay, but it's just going to be small. So this is always less than 1% of the background conductance, maybe 0.1% or less of the background conductance. So you need second harmonic to pick it up. So the next thing that people used was Andreev reflection. So this happened in the 80s, where people started to apply the Bogoliubov-Dijen equations to interfaces. And there's a very well-cited paper by Blonder, Tinkham, and Klaptwick, where they actually looked at what would happen if you went from the tunneling to the clean regime. And they were able to define, this is just a simple, blind application of the Bogoliubov equations. If you have electrons injected into an I-beam film, and this is taken one by my undergraduates. It's beautifully modeled. It gives you the gap. It gives you the gap symmetry. It gives you a whole bunch of information about the superconducting properties. And this can be a big effect because, in fact, Andreev reflection can be as much as 100% reflected. So this could be a big effect, but so that's understood. So we started doing this stuff, and this is just an example in serum cobalt-indium-5, which is a nice, cute little heavy fermion superconductor, and we notice this anisotropy here. Now, I won't have time to go into this, but Harrison's theorem said this, you can't have this anisotropy. And I was torn up by some very famous people, like, what's wrong with you? Junctions are bad. And then we finally figured out the problem. And so I want to just go into, I'll go into this one now. And I think rather than going to the heavy fermions, I want to talk about the iron-based superconductors. So this one will show how we pick up the electronic nematicity. Here is the most studied of the iron-based high-temperature superconductors: barium, iron-2, arsenic-2 with cobalt doping. And that's what we have domed, okay? It's about 23 degrees TC. Way up here, it's paramagnetic and tetragonal. As you go down in temperature, first you go through a structural phase transition, and then antiferromagnetic, and down here it's antiferromagnetic and orthorhombic. And my student Hamoud Aram, I said, hey, we don't know what's going on in this point contact stuff. See if you can pick up what's going on at these phase transitions here. Because we didn't know from nothing, okay? We didn't know what to expect. So he goes and measures this stuff. Let me just show you. He's looking at the parent compound. This is 135 degrees and no superconductivity. And these are some data where it shows at 175 degrees, we see a funny shaped background conductance. And as we lower the temperature, we start getting enhanced conductance around zero bias. Just to be perfectly honest, we don't understand the upturn in the background conductance nor that dip in the center. We have an idea what it is, but don't look at that. Now that I've told you that, that's all you're going to look at. Anyhow, concentrate on the enhanced conductance here. Now what I'm going to do is sit right here at zero bias and look at that as a function of temperature. This, remember, is the normal state. This is the parent compound. There's no superconductivity there. We see the zero bias conductance sails right through the structural magnetic phase transition and just keeps coming up. It's got that dip in the center. Okay? We don't see these phase transitions, but we see something turning on at 175 degrees. Hamoud went through probably thousands of spectra by the time he got his PhD. But he found out where he got this excess conductance and where he didn't. And he took a lot of data like this, which shows this excess conductance around zero bias, plus the Andreev reflection in the center. So if you could take this and model it to see the quality of the Andreev reflection, that was helping to determine our diagnostics to making sure we had good point contact junctions. Now, this is something that I think really set the stage for us trying to figure out what was going on theoretically. So this is our phase diagram. The points of showing the structural phase transition, the magnetic phase transition, and the superconducting phase transition were all taken by Hamoud, and they were taken by looking at resistivity. If you do resistivity versus temperature, you can see those transitions. There are always kinks in the resistivity versus temperature curve. What you don't see is anything that has to do with the nematicity. When you measure these materials using point contact spectroscopy in the right regime, you actually don't see these transitions here, and you only see the onset of the nematic. So we see right now, in your face, resistivity and point contact spectroscopy are different measurements. They're picking up completely different things. So what we did is we went through and measured a whole bunch of things, and we found out if other people saw electronic nematicity, we did too. If they didn't, we pretty much didn't either. So we knew it had something to do with it. And then enter Wei-Ching Li, who came up with a theory. And it's a theory worked out with Philip Phillips, which is an orbital ordering. And I won't go into a whole lot of detail, but it's pretty straightforward in some sense, which is looking at how so this is the orbital structure. You have a dxy at the top, dxz, dyz, and eg orbitals at the bottom. And as you lower the temperature, you're going to start depopulating the xy orbital and start populating the yz and the xz. And so if it's completely tetragonal, those things must be at the exact same value. They have to be degenerate. But as the electrons fall from the xy into the xz, that will get larger, because if the electron falls in a certain orbital, that orbital must get larger because the orbital size is proportional to the occupation. So if I've lost you, that's fine, but let me just tell you, you're now going to get an oscillation of these orbitals as you lower the temperature. And each time, these are all getting elongation, and they're breaking the C4 symmetry. Then he did something which I don't know what to do, is that he calculated the self-energy and showed that you expect a peak of the density of states around zero bias. So for the first time, we had something that said, hey, we may be measuring a density of states coming from electronic correlations. And so then he went on to do this next thing, which I worked with him on this a little bit, which he was able to then show, take the self-energy that he calculated, I just showed you, from the orbital fluctuations, and plug it into some known theories using the Keldysh they call it Schwinger-Kadanoff-Boehm-Keldysh formulation, and show, in fact, he did generate the spectra that we measured. So for the first time, we have a closed loop and show how this point contact spectroscopy specifically picks up a density of states arising from non-Fermi liquid behavior. Why didn't we see the structural and the magnetic phase transitions? Well, there's a little picture. I'm going to have to use words. Remember, to get a good spectroscopy, the little aperture has to be really small. If it has to be really small, you're going to have a large momentum spread. Delta X, delta P, less than h bar over 2, right? So when you do the point contact spectroscopy, the electrons that come in cover a large fraction of the Fermi surface. The phase transitions that I showed you a couple of slides ago, whether it's structural or magnetic, are simply simple Fermi surface reconstructions. So you get more electrons here, you get a doubling or halving of the unit cell, but you have the same number of electrons. So since we're just measuring scattering on the Fermi surface, and we have no momentum resolution, we don't pick that up, or very little momentum resolutions, we don't pick that up. So now we see the point contact does pick up correlations, but doesn't see simple Fermi surface reconstructions. So it's a filter for correlated electron behavior. I'm not going to go into this because I want to finish this up, only one more slide, okay? So this is what we're doing in our Center for Emergent Superconductivity, and we're having some success filling a metric. When the president came out with ideas, the idea of having a materials genome initiative in the United States, the original ideas were geared toward hard materials, semiconductors, things that we knew how to calculate, things that we had a genome for. There is no genome for correlated electron materials. So we can't have someone tell me, this is the structure and these are the elements, make those into a solid and it'll be a superconductor. So what we're doing is that's the reverse source. We're doing the forward source problem, which is we're going to start with, and we've done a lot of this, and writing papers on it, but we don't have a new superconductor yet. So we have basically chosen which chemical motifs we think would be interesting to use, and then identify certain structural types. Now we have, working with Lucas Wagner and other people, we go through the entire crystal index and find things that are interesting that have empty ternary diagrams. That's one thing that we're doing. And then we do a whole bunch of DFT and see which materials we think might be interesting, and we start to make these things. When the DFT fails, and it fails, right? We all know DFT isn't perfect. They're applying some quantum Monte-Carlo to try to tweak these things up, and we're hoping that'll lead into helping to give better basis on finding what to use in DMFT. But this is what we're doing right now, and we're growing things, okay, based on this. And we may have a new material. But if we actually do get a new material and we find something that looks good, and we're measuring stuff right now, we will throw everything at it. you have my promise that we're going to actually measure it any way we can. But one thing that might be useful is this point contact spectroscopy, because if we get that excess conductance, then we know we have that electron matter, and that may give us some confidence to do the doping studies of that material. And I think I should finish now. And so conclusions and future directions is that this is really fun. This is really a hard problem. I think it's the hardest problem that exists in physics today. I think, who's the high energy guys here? I think it makes looking for the Higgs look like a walk in the park, because you knew what you were looking for. We don't know what we're looking for, okay? And so, by the way, I said that at the Snowmass meeting, and we all got, you might have been there, we all got along. It was okay. I came out alive. And so we need better superconductors, and we want to understand these things. And so let's all work together and try to create materials by design. And I thank you for your time.
Okay, Laura, you're going to have to work on being provocative for your next colloquium.
I'm being what?
You're going to have to work on being provocative for your next
Okay.
colloquium. So, questions for Laura? John.
You showed one plot where it was like normal kind of superconductors, niobium-310 and so forth, and it was plotted versus time going up. Now that says more about us than about the superconductors, right?
Well, those are, but what you're doing, you're choosing it that way. That says more about the people that wrote that plot than actually us. Because what we're looking at, this is really the highest TC that was discovered at that time. So there's a lot of low-temperature superconductors that are discovered all the time, like today, right? So people are still finding TCs down here, but these are the highest TC of that year. So that's how they're picked. So. And the other thing which I like to point, there's no organics on here. There's huge numbers of families missing. And these little twiddles here drive me crazy, because it actually is a pretty linear plot with those twiddles aren't there.
So if you look at the wave function orbitals, the wave function symmetry, do you have a prediction about, other than D-wave, what we should be looking for?
No. I mean, all we know is the highest TC superconductor is D-wave, but in some sense that's quite detrimental to applications, because if you have any scattering within the material, you break pairs like crazy. And if it's an S-wave superconductor, you don't break pairs. Some of the work that we've done in the center is taking the iron-based superconductors and putting pinning centers in them, a lot of pinning centers, and finding that the TC is not going down much. So that's, in some sense, it's great for high TC, but it's terrible for high JC. So, there was a question back there?
What's the length scale for the non-accessible?
The only people that I know that have a length scales, there's some work done at low temperature with STM, and the length scale is about a lattice constant wide and eight iron lattice constants long. And there's nothing in the crystal structure that says that should happen. Weird. What is going on there? Okay.
All right, thank you again.
Thank you.